Log on, tune in, find out. Another good idea from Cambridge.
To introduce the first speaker of our Sydney series, Anthony Henderson, who will tell us about the geometry of the exotic nilpotent cone.
Thank you, Pramod, and I'd like to thank the organisers of the whole program for inviting me here and giving me the chance to speak. So Meinolf and Sasha, thank you very much. Gerhard doesn't seem to be here, but thank him too. And Pramod's not entirely selfless in giving me this seminar, because I'm going to be speaking about our joint work, which is this middle paper here, Orbit Closures in the Enhanced Nilpotent Cone. But first I want to talk a little bit about the paper by Sue Kato, which led to it in some sense. So the plan for the talk, which hopefully won't run for too long, is that first I'll be talking about the Springer correspondence in type C to remind you of how things work or worked in the classical, so to speak, picture. Then I'll talk about Kato's exotic version of this, and then the enhanced nilpotent cone, which is what Pramod and I studied, and how it relates to Kato's geometry. And I'll conclude with some more speculative remarks about a possible theory of exotic character sheaves of type C and what that might mean. So first, to remind you about the ordinary Springer correspondence, throughout the talk I'll be living in the type C world, so this notation will apply all the time, that V is a 2n dimensional vector space with a symplectic form. I'll write G for the general linear group, so it's GL2n, and K for the symplectic group. And so of course the Lie algebra of G is just endomorphisms, the Lie algebra of K is anti-self-adjoint endomorphisms. So that means that they satisfy this. Oh, that wasn't right. Hopefully. Thank you, Steve. So the nilpotent cone in this, the ordinary nilpotent cone is just the nilpotent endomorphisms in this Lie algebra of K. And the orbits in these were parametrized or described a long time ago by Tim Wall and also by Hesselink. I'm not sure exactly about who deserves the credit for which of these statements that I'm saying here. But the K orbits are in bijection, completely classified by their Jordan form. So that's a partition of 2n, and the only partitions which can arise for an endomorphism in the symplectic Lie algebra are the ones where odd parts have even multiplicity. So that's this particular class of partitions of 2n, which I'm calling P2nk. And it's nicer than that. You also have that the closure ordering is exactly the dominance order on partitions. So the geometry of this ordinary nilpotent cone of type C is well described by just this set of partitions with this combinatorial dominance order. So that's nice, but it's not quite as nice as it could be, because of course you remember in type A, the situation's even better, because the GLN orbits on its nilpotent cone are in bijection with partitions of n, and that's in bijection with irreducible representations of the symmetric group, which is the Wahl group of GLN. So you have this perfect bijection between orbits in the nilpotent cone and irreducible representations of the Wahl group. And this result says that this doesn't happen in type C, because the irreducible representations of the Wahl group, so which in this case is the Reith product of the symmetric group with the group with two elements, are in bijection with various things. One way to parameterize them is to use the set I'll call Qn, which is the set of pairs of partitions of total size n. But if you want to parameterize it by partitions of 2n, those are naturally in bijection with the partitions of 2n which have an empty 2-core. This bijection here, you could take a partition of 2n and take its 2 quotient, and that would be one of these. And that condition of having empty 2-core is weaker than the condition of having all the odd parts occur with even multiplicity. So there are more representations of the Wahl group than there are orbits in the nilpotent cone. So it's not quite as simple as the type A case. Okay, but as you probably know, there is a way to actually find all the irreducible representations in terms of the geometry of the nilpotent cone, and that's the Springer correspondence. the way it works is that you look at the Springer resolution of the nilpotent cone. So you take the Borel subgroup of K, Bk, and take the vector bundle over the flag variety determined by its nilpotent radical and map that to the nilpotent cone. And that's a resolution of singularities. So I've written out there more in a more low-tech way what the fiber of this resolution is. If you just have a nilpotent X, then the fiber over that nilpotent is just all the flags in the vector space, which are isotropic in the sense that the perpendicular of the I-dimensional space is the 2n minus I-dimensional space. And these flags have to be preserved by the nilpotent. So that's all the Springer resolution is in this case. And then there's the beautiful facts about the Springer resolution, which most of this is true for all types. And various parts of this were proved by Springer or Lustig or Boho and McPherson. Firstly, that if you take the trivial constant sheaf on this resolution and push it forward in the derived sense, you get something whose endomorphism algebra, so that's a complex of sheaves, and its endomorphism algebra in the derived category on the nilpotent cone is isomorphic to the group algebra of WK. So this, if you like, is a very long-winded geometric construction of the Wahl group. And it has the consequence that irreducible representations are in bijection with the simple summands of this complex of sheaves. And those are intersection cohomology complexes. So each one is attached to an orbit and an equivariant local system on the orbit. And these equivariant local systems are what explain the difference between type A and type C, because you have these extra representations which don't correspond to an orbit themselves, and what they go to. So if a bipartition of n does correspond to a partition of 2n in the right set, then that irreducible representation just corresponds to that orbit with the trivial local system. Otherwise, you have to modify the partition to make it an allowable partition for the symplectic group, and then you get a non-trivial local system. So the upshot is that the irreducible representations are in bijection with some set of orbits and local systems, but it's not quite as simple as you might think, because not all the possible local systems arise. So again, there's something slightly unsatisfactory about this. So Cato's exotic Springer correspondence is a different version of this kind of idea, where a lot of these complications go away. What he does is consider a different representation of the group, first of all. So you look at the K-invariant complement of the Lie algebra inside the Lie algebra of this bigger group, the general linear group G. So in other words, instead of taking anti-self-adjoint endomorphisms, you take self-adjoint endomorphisms. And the nilpotent cone in that just means the nilpotent self-adjoint endomorphisms. So that's a nilpotent cone in a symmetric space, or a nilpotent cone attached to a symmetric space. And these were studied, of course, by Costant and Sekiguchi and Rallis and people like that. So I think the parametrization of orbits in this case could be credited to either Costant or Sekiguchi. That, again, the orbits in this space of self-adjoint nilpotents are parametrized by Jordan form. And the partitions of 2n which occur here have to have the property that all parts occur with even multiplicity, not just the odd parts. So that means, of course, that you can just halve all the multiplicities and just get a partition of n. So effectively, these are in bijection with partitions of n. And again, the closure order on the set of orbits corresponds to dominance of partitions. So the geometry is, again, very simply described in terms of combinatorics. And in the Costant-Sekiguchi philosophy, nilpotent cones attached to symmetric spaces like this should correspond to nilpotent cones in real Lie groups. And for this particular symmetric space is meant to correspond to the general linear group over the quaternions. So you're meant to think of this as some sort of analog of the nilpotent cone for the quaternions, and that sort of explains why the orbits are parametrized by partitions of n, because they have a quaternionic Jordan type, and that would be a partition of n. So Cato's exotic cone is not this, however, but this nilpotent cone in this symmetric space G mod K multiplied by the vector space. So he considers the variety of pairs of a vector in the vector space and a self-adjoint nilpotent endomorphism of the vector space. And that's the exotic nilpotent cone of type Cn. So a few remarks about his cone, which helped to explain why you would consider this particular variety. First we have Kato's result. So Kato finds a resolution of his cone similar to the Springer resolution. So now I've written it out on the top line there in sort of symbolic notation, but I've also written out exactly what the fiber of his resolution is. So he now has a pair of a vector v and a nilpotent x, and he considers flags, which are again flags in the 2 n-dimensional vector space, again isotropic. And the new condition now is that they have to, I might use the pointer, they have to, the vector that you're fixing has to be contained in the middle dimensional space, so in the Lagrangian subspace in this flag. And the flag again has to be preserved by the nilpotent endomorphism. And once again, he proves that this resolution has the nice property that when you push forward the constant sheaf, the trivial constant sheaf in the derived sense, you get something whose endomorphism algebra in the derived category is isomorphic to the group algebra of WK. So this is another, sorry? Oh, sorry. Yeah, so V plus, well, if you write it this way, you have to choose a Borel subgroup. So that's effectively choosing an isotropic flag, and then V plus would be the middle dimensional subspace of that isotropic flag. So I'm calling it V plus because that would be the span of the weight spaces whose weights were proportional to positive roots. Yes, so we have actually a second geometric construction of the group algebra of the Wahl group of type C. You can not just use the ordinary Springer resolution, you can use this other resolution of this other sort of exotic nilpotent cone, as he calls it. And the really nice thing is that this one is better. The second one is better in the sense that the simple summands of this push-forward complex don't involve any local systems. I mean, all the local systems are trivial. You get all the intersection cohomology complexes of the orbit closures with trivial local systems, and what's more, all the orbits occur. So you have, again, the same situation as we had in type A, where the orbits in the nilpotent cone are exactly in bijection with irreducible representations of the Wahl group. So here, the K orbits in his exotic nilpotent cone V cross NGK are in bijection with this set Qn of pairs of partitions total size n. So, and again, just as in the type A case, if you want to realize geometrically one of the irreducible representations of the Wahl group, so call it rho mu nu, that's the irreducible representation corresponding to mu nu, then you can find that exactly as the top degree cohomology of one of these Springer fibers. So you take a pair Vx in the corresponding orbit, and the Springer fiber of that, and the top cohomology of that carries a representation of the Wahl group WK, and that's irreducible. There's no business with splitting it up according to representations of the A group or anything like that. So in short, the exotic Springer correspondence that Kato constructs is more like this clean picture in type A than the ordinary Springer correspondence is. So why did this work? Well, it seems like magic. Why this particular variety, and how did he think of this in the first place? Well, one obvious point is that this cone that he's considering is the Hilbert null cone in a representation of K. So the ordinary nilpotent cone is the Hilbert null cone in the adjoint representation. That means all the points whose orbit closure contains 0. And this is the Hilbert null cone in a representation of K as well. It just happens to be a reducible representation. If you take the vector representation direct sum with this quotient of the bigger Lie algebra by the Lie algebra of K. Well, that seems like a funny thing to choose, except that the weights of this reducible representation are almost the same as the weights of the adjoint representation. You have here, V has weights in the ordinary way of talking about weights. The weights of V are plus or minus epsilon i's, whereas in the root system you have plus or minus 2 epsilon i's. And so the long roots of the adjoint representation have been cut in half, and those give you the weights of this representation. And the short roots and the zero weight space of the adjoint representation remain. They're the weights of this representation there. So in some sense, this construction was only possible because it happened that the long roots in the root system of type C were divisible elements of the weight lattice. You could divide them by 2 and get something almost the same. So in fact, in every other type other than A and C, the highest root is a fundamental weight. So you're never going to have that same sort of thing happening in other types, which is sort of partly an explanation for why this phenomenon, at least in this very nice form, occurs in type C and not in other types. Like the ordinary nilpotent cone, Kato's cone is a complete intersection. It has the same dimension. So, of course, since I said the weights of this are almost the same as the weights of this, the dimension of these two representations are the same. They're both 2n squared plus n. And both of these nilpotent cones are cut out by n equations. So they're complete intersections of both of dimension 2n squared. In particular, they're both normal varieties. One very nice feature of Kato's case is that the so-called A function equals the B function. That if you take an element of his exotic nilpotent cone in the orbit corresponding to the pair mu nu, then the dimension of his version of the Springer fiber, which you might call the Kato fiber, this fiber that I talked about on the previous slide, so that's the A function of this element, equals the B function, namely the smallest degree in which this irreducible representation of W occurs in the covariant algebra. So that's given by this combinatorial formula involving the n, which is the B function in type A, 2n of mu plus 2n of nu plus the size of nu, which you can find in Meinhoff's book, for instance. So the A function equals the B function, which is, of course, something which doesn't happen in the ordinary Springer correspondence. The dimension of each orbit is also given in terms of this B function. So this is effectively just saying that the resolution is semi-small and exactly so, that the dimension of the fiber is always half the codimension of the orbit. So the dimension of each orbit is 2n squared minus 2 times this B function. And the point stabilizers of points in this cone are connected, just like in type A, which is why no non-trivial local systems arise. It's expected, although neither Kato nor I have been able to prove this yet, that the inclusion of one of his fibers inside the whole flag variety induces a surjective map on cohomology the other way. This would, in some sense, explain point 3, because the cohomology of the whole flag variety is the co-invariant algebra. And so this would sort of make it reasonable why this irreducible representation rho mu nu, which is meant to be the top cohomology of this fiber, does occur for the first time in that particular degree of the co-invariant algebra. So that's a feature which happens in the ordinary Springer fibers for type A, but not in type C. So yet another respect in which this exotic situation is more like the ordinary type A. And finally, so this is a major topic to be cramming into one point on this slide. This was actually Kato's real motivation, was that he was able to use this cone to construct an exotic Deligne-Langlands correspondence. So there's not only a nilpotent cone, there's also an analog of the Steinberg variety. And if you consider the appropriate equivariant K-theory of that Steinberg variety, you get a geometrization of the affine Hecke algebra of type C with unequal parameters. And this, of course, was a case that wasn't covered by the standard geometrization using the ordinary Steinberg variety. So this was partly his motivation in studying this in the first place. And so, I mean, he's got many important results out of this, which I won't go into because my main concern here is about the geometry of just the nilpotent cone. So much for Kato's construction. Are there any questions about that before I move on to the contributions of Pramod and myself? Yes, Cedric. That's a good question. What kind of unequal parameters occur? I'm afraid I'm going to get it wrong if I try to guess, but yeah, anyway, so I have a copy of his paper here if you'd like to consult it. Any other questions? Any ones I can answer? Okay.
Those things have nice affine pavings.
Okay, so John's question is about affine pavings. You mean of the resolution fibers. So that's a very good question, and one I would like to know the answer to. In the analogous case of the enhanced nilpotent cone that I'm about to move on to, Pramod and I proved the existence of affine pavings of the fibers. And we haven't yet managed to prove the analogous thing for Kato's cone. And he himself also tried quite hard in writing his paper, and in the end he had to prove the vanishing of odd cohomology by a different argument. So it's an open problem, and I'm hoping to get around to doing it soon. I mean, I have no reason to believe it's not true, and I have good reasons, I think, to believe that it should work. So not only should these fibers have affine pavings, but I would expect that all the affine spaces involved would be even dimensional, as for reasons I'll explain in a moment. Well, I mean, the reason is simply that this, what I'm saying here in this first sentence here, that the Kato's construction is somehow meant to be a quaternionic thing. I mean, this nilpotent cone in the symmetric space G mod K is meant to be somehow like the nilpotent cone for GLN over the quaternions. And multiplying it by this 2n dimensional vector space, I guess, is something like multiplying it by an n-dimensional vector space over the quaternions. So Kato's cone is sort of meant to be like a quaternionic version of what you would get over the complex numbers if you just took the n-dimensional vector space multiplied by the ordinary nilpotent cone of GLN. And that's what Pramod and I call the enhanced nilpotent cone of type A. So that just consists of pairs of a vector in an n-dimensional space and a nilpotent endomorphism of that n-dimensional space. So this is the Hilbert null cone, again, of a reducible representation. If you take the vector representation direct sum the Lie algebra for GLN, then you get this enhanced nilpotent cone. And to anticipate the answer to John's question, we've proved that the fibers for the resolutions of this enhanced nilpotent cone have affine pavings, and I suspect that the fibers for Kato's cone should be exactly the same in some sense, but with all the complex vector spaces or complex affine spaces replaced by quaternionic affine spaces. So they should then be even dimensional as complex affine spaces, something like that. So this is what we first proved about these things, and this was actually independently proved by Roman Travkin, a student at MIT, who was working on this enhanced nilpotent cone for a completely different reason. So the first order of business was to find the classification of orbits, and really Kato had almost done this himself in the course of studying his own cone. But it turns out to be the same answer as in his case. The GLN orbits on this variety of pairs are again in bijection with the set of pairs of partitions of type N. So this is a slightly remarkable statement because, after all, the set of parameters, this Qn, looks like a type B sort of thing, and yet at the moment, on this slide, I'm talking about completely type A geometry, just a vector space and nilpotent endomorphisms. There's no symplectic form, there's no orthogonal form, there's nothing like that. The group is GLN, and yet the parameters are this type B set. So here's how the parameterization works, or one way to describe it. If you want to know which pairs Vx correspond to the pair of partitions mu nu, you look at a particular subspace of the vector space. Namely, you take all the endomorphisms which commute with x. That's what I mean by putting x in the superscript here. So this n, c, and x is the centralizer of x. And apply that to the vector. And that's a subspace of the vector space on which x obviously acts. And x induces a nilpotent endomorphism of this subspace and also of the corresponding quotient. So the first partition mu tells you the Jordan type of the endomorphism of this subspace, and the second partition tells you the Jordan type of the endomorphism of the quotient. So it follows that the Jordan type of the whole of x is given by the sum of the two partitions in the partwise sense of sum. And we also showed that the dimension of the orbit is given by half what it is in Kato's case, n squared minus this b function. And again, the point stabilizers are connected, so there can't be any equivariant, non-trivial local systems. So the one thing that you'll notice I haven't mentioned there is about the closure order. So in all of the previous cases where we've had a parameterization by partitions, the closure order corresponded to dominance order on partitions. Here we've got a parameterization by pairs of partitions, and there are various partial orders floating around on that set. So it was natural to wonder what the correct partial order was that corresponded to closure order of these orbits. So we actually proved this not just for our cone, but for Cato's cone as well. And there's a connection, namely that Cato's orbit corresponding to mu nu. So remember, in his cone, which is V cross the nilpotent cone of G mod K, so that's pairs of a vector in a 2n dimensional space and a self-adjoint nilpotent. But you can, of course, consider that as part of the enhanced nilpotent cone in that vector space. So just a 2n dimensional vector space times all 2n by 2n nilpotent matrices. And his orbit is just the intersection of his cone with the enhanced nilpotent orbit corresponding to the pair of partitions where mu is doubled and nu is doubled. So every part of mu occurs twice and every part of nu occurs twice. So that's how you get those shapes, again, which have the even multiplicities like the ones you expect to have. So that means that our result about closure order was able to be proved to both cones. So this is one of the main results in our paper, that the closure order in both Cato's exotic nilpotent cone and the enhanced nilpotent cone of type A corresponds to this partial order on pairs of partitions. So it's a partial order which, in some sense, privileges the parts of the first partition over the parts of the second. So whereas in ordinary dominance of partitions, you add up you have the first part of one partition less than or equal to the first part of the other, then the sum of the first two parts less than or equal to the sum of the first two parts of the other, and so on. Here, you compare the first part of the left partition, then the sum of the first parts of left and right, then first of left plus first of right plus second of left, then first of left plus first of right plus second of left plus second of right, and so on. So you always are comparing, you're sort of moving from across the rows from left to right before you go down to the next row. And you never involve quantities such as rho 1 plus sigma 1 plus sigma 2, for instance. It doesn't affect the partial order. So one of the points involved in proving this was we needed some sort of interpretation in terms of these nilpotents of what these quantities mean. Well, so half of these equations are sort of easy to interpret. That inequality there and that inequality there and all the ones in even positions just tell you that rho plus sigma, which is the type of the nilpotent here, is dominated by the type of the nilpotent here. So that part of the partial order is easy to understand. What's more interesting are these other rows, where these other inequalities where you have an asymmetry between the two partitions, such as that one. And the reason that those come up in some sense is that these quantities that you get here, where you add up the first k parts of each partition and then add on the k plus first part of the first partition, the interpretation of that is that it's the maximum possible dimension over all choices of k vectors of the submodule, the x submodule generated by those k vectors together with the fixed vector v. And once you find that sort of interpretation of this quantity, you can use that then to prove that at least one direction so I mean, if you convince yourself that this sort of quantity will be upper semi-continuous or lower semi-continuous, I never know which way around it is, then you've proved one direction of the theorem, that the closure order implies, well, I can't even think which way around the theorem is, but either you've proved that the closure order implies that these inequalities hold, or you've proved that these inequalities imply the closure order. Now, this partial order had turned up before. Of course, it's not surprising that such a natural sort of definition, slightly asymmetric but otherwise fairly natural definition, had arisen before. And the place that it had arisen before was in a paper of Shoji's, where he studied what he called limit symbols. These are meant to be generalizations of the combinatorics that arise in talking about Springer correspondences and things like that. So it's not surprising that they would have arisen there. And one thing that showed, before I go on to that, I'm giving you just a little picture of part of this partial order in the case n equals 4. So these are just the sort of large orbits, the orbits of codimension at most 6. So the whole enhanced nilpotent cone has dimension n squared, 16 in this case. And in this picture, what we've done is put the two partitions back to back with a dividing line in between them. So this black vertical line divides the two partitions, and on the left-hand side of that, you've got the Young diagram of one reversed, so right justified, and on the right-hand side, you've got the Young diagram of the second partition, left justified. So you can see, if you want to play around with this partial order, that there are various different kinds of covering relations. You have covering relations where the total partition doesn't change, such as if you look at those 6 orbits there, those are all all orbits where the nilpotent has type 3-1. So the total partition in all of those is 3-1. And all you do when you have a covering relation in this is that one box moves in the same row from the left-hand side of the wall to the right-hand side of the wall. So here, a box has moved from the left-hand side to the right-hand side in the first row. In this covering relation here, a box has moved from the left-hand side to the right-hand side in the second row. So those are the sorts of covering relations which don't change the type of the nilpotent. Then there are other types of covering relations which do. You could, for instance, as you see here in this covering relation, a box has moved from the right-hand side down to the left-hand side. So that happens. And then boxes also move from boxes also stay on the same side of the wall, occasionally moving down. I think I've got an example of where a box moves down on the left-hand side of the wall there, to give you that closure relation there. And there's probably an example there somewhere also of where a box moves on the right-hand side. Maybe not among these orbits. But in any case, you see there are various things to say about this partial order. One interesting point is that it's not self-dual, this poset. There is a natural duality on the set of parameters, of course, because they correspond to irreducible representations of the Weyl group. So if you tensor the irreducible representation by the sign, that corresponds to swapping the two partitions and transposing them both. And this partial order is not reversed by that involution. However, if you look at just the bipartitions which correspond to special representations of the Weyl group, then I believe it actually is that involution does give a duality of that poset. Perhaps that's not unexpected because, of course, that happens with special orbits in the ordinary nilpotent cones, the types B and C. Okay. One other thing, more obvious point to point out is that there are orbits of odd dimension in this cone, whereas in the ordinary nilpotent cones of types B and C, all the orbits have even dimension. So in particular, you have closure, you have orbits, the boundaries have codimension 1 in general. So you have orbits of codimension 1 inside a bigger thing. And this raises some interesting questions about the singularities of these orbits, of the orbit closures, I mean. Okay, so back to Shoji's work. What he actually did was, having defined this partial order, he then ran the so-called Lustig-Shoji algorithm on this set Qn with this partial order. This is something you can do whenever you have a partial order on the set of irreducible representations of a Weyl group. It produces some polynomials, and they generalize the Koska polynomials, which is what happens if you do it with the poset of partitions of n. And just like Koska polynomials in the type A case give you intersection cohomology of nilpotent orbit closures, we proved that Shoji's Koska polynomials, which are parameterized by pairs of bipartitions, tell you about the intersection cohomology of orbit closures in the enhanced nilpotent cone. So, firstly, the intersection cohomologies only live in even degrees, just like you would expect from the ordinary cases. And then if you put the dimensions of the even degree cohomology sheaves of these IC complexes together in a polynomial, you get exactly Shoji's polynomial. The normalization here is a little bit funny. You would sort of expect that 2i really to be just I by strict analogy with Lustig's case, and I mean with the type A case. And the reason for that is that really the correct analogy with the type A case should be this result for Kato's cone, not for our enhanced nilpotent cone. There is again a sort of doubling relationship that we believe is true. I think I've said that next. we expect that the intersection cohomology of orbit closures in Kato's cone is going to be given by the same polynomials. It's just that there all the degrees will double because of this phenomenon of effectively going from the complex numbers to the quaternions. So that certainly happens if you forget about the vector space part. If you just look at the nilpotent cone attached to the symmetric space G mod K, the IC of the orbit closures in that is given by the same Koska polynomials as give the IC of orbit closures in the type A nilpotent cone, just with all the degrees doubled. By the way, Shoji hadn't previously known or proved the fact that the coefficients of his polynomial were positive, but of course it follows from this. And there probably should be some combinatorial interpretation of these coefficients as well, but I don't think anyone's looked at it. So something involving contents of tableaus or something. I don't know.
Or multiplicity?
I'm sorry?
Multiplicities of representation.
Fake degrees. Well, I mean, so in some sense, this is all working with the ordinary fake degrees. Yes. So the in the enhanced nilpotent cone, we don't have any group acting on the cohomologies of the fibers. In Kato's case, he does. He has this Weil group of type C. Now, if the relationship between the two cones is what I expect it is, then it would follow that the multiplicities of representations in the cohomologies of his fibers are given by exactly by the fake degrees.
But doesn't this endomorphism bring this push forward, like algebra or something? Or is that
No, not in the enhanced nilpotent cone. No, that's what's sort of missing in this enhanced nilpotent cone picture is that equivariance with respect to a group. I mean, because we've sort of cut everything in half, and somehow that's destroyed the action of the Weil group of type B that used to act, the Weil group of type C. I mean, we have an action of the symmetric group, but a sort of boring one. I mean, you could act by the symmetric group effectively just on the nilpotent cone part, ignoring the fact that you've multiplied by the vector space. But there's nothing interesting that comes out of that. Eric, did you?
Can you clarify? So this is the Lustig-Shoji for type C?
Yes, that's correct. Lustig-Shoji algorithm for type C. So, I mean, this set is in bijection with the irreducible representations of the Weil group of type C. So you use the fake degrees for that group in running the algorithm. Yeah.
And you group just by B function?
Oh, you don't. Oh, sorry, you don't group at all. You're trivial families. Yeah. So that's the nice feature that I mean, that makes this just like the type A case. You have no families or anything. Yes. Okay. Are there any other questions? All right. So now for the more speculative part. The fact that the Lustig-Shoji algorithm is involved in this, and the fact that the families are trivial, leads me to suspect that there's some theory of exotic character sheaves of type C, which is going to be closer to the type A theory of character sheaves than the ordinary type C character sheaves. And I expect, so here's a sort of definition of what some of these exotic character sheaves should be. So I'll just give the definition of what the unipotent exotic character sheaves of type C should be. So this is the same notation as I've been using throughout. So V is this 2 n-dimensional symplectic vector space. G, however, is the whole general linear group. So these character sheaves are going to live here, but they're going to be equivariant for K cross K, where K is the symplectic group. And one copy of K is going to act diagonally on the left of these things. Another copy of K is going to act by right multiplication just on the G. So you could divide out by that second copy of K and just think of it as K equivariant sheaves on V cross G mod K, if you like. So that's where I think these exotic character sheaves are going to live. And I want to define them by this sort of diagram, which sort of follows the whole philosophy of Ginzburg about how to define character sheaves on symmetric spaces. So there should be, you should start off with a K-equivariant perverse sheaf on V cross the flag variety. So remember, this is the flag variety of GL2N, not K. So K acts on that V cross G mod B, and you start off with a equivariant simple perverse sheaf there, and also another one just on G mod B. Pull them back take the tensor product, pull it back in a derived sense to this variety V cross G mod B through this map Q, where you can read what it does there, and then push them forward through the projection which forgets the flag variety. So this is just by formally following the constructions that have been done in similar situations. I think this should be the definition of unipotent exotic character sheaves, and then if you want to modify it to get other central characters, so to speak, then you'd have to take coverings of this by the torus and that sort of thing. So part of the motivation here is that there is a theory of character sheaves on Cn cross GLN. This is the theory of mirabolic character sheaves, which has been written about by Finkelberg and Ginsburg in a couple of papers, one just by them and one joint with Travkin. And those character sheaves arose, this is why Travkin was interested in the enhanced nilpotent cone in the first place. These character sheaves arose because if you study representations of the trigonometric Cherednik algebra by some sort of localization procedure, which I don't claim to understand, those representations are the same as D modules on this space, and then by the Riemann-Hilbert correspondence, they correspond to these character sheaves. So they had a very similar diagram, so I'm not claiming much originality in thinking up this definition. This is what it should be if it's going to work at all. However, I have no idea if you define character sheaves this way on this space, I have no idea what the corresponding D modules have to do with representations of anything. I don't know whether there might be a type C version of Cherednik algebras or something like that, which might play that role. So if you want to build a theory of character sheaves like this, then one of the main results is going to be the classification of character sheaves. And there should be a classification by cells, something like the ordinary one. And what that would mean geometrically would be the following. You'd have to firstly consider the K-equivariant simple perverse sheaves on V cross G mod B and develop some theory of cells for those. And Travkin has done something very similar for the case relevant to the mirabolic character sheaves, which is the case of GLN equivariant simple perverse sheaves on Cn cross two copies of the flag variety of GLN. So the orbits in that case, of course, if you didn't have the Cn there, the orbits are parametrized by permutations in the symmetric group Sn. So when you put the Cn in, you have to decorate the permutation in some way to show how the vector relates to the two flags. And so he's developed in the last paper I've written up there, the mirabolic RSK correspondence. He's developed nice combinatorics of these parameters and shown how you get a theory of cells out of it by an algorithm which is very similar to the Robertson-Chenstedt algorithm, but with suitable modifications for this decoration. It's actually a lot harder than it sounds. I mean, it must have taken quite a bit of work to find the right algorithm because it's not that obvious. So I suspect that something like that might be true in this type C setup. And just as a sort of tantalizing result in this direction, or actually just a conjecture, because we've only checked it up to n equals 3, Peter Trapper and I reckon that the orbits, the k orbits on this product of the vector space and the flag variety of GL2n are in bijection with pairs of a bipartition and a standard Young tableau whose shape is the total shape of the bipartition. And notice the sum shape of mu1 plus mu1, mu2 plus mu2. And then the cells are just going to be given in the usual sort of way by varying the tableau but keeping the bipartition the same. So the cells are going to be in bijection with these bipartitions that arise, but it's not going to be all bipartitions in Qn. What it seems to be is the ones which have the same number of odd columns on both sides of the wall. So the total multiplicity of odd parts in the transpose partition of mu is the same as that for nu. So one way to think of, if you fix the total partition and want to split it up as the sum of mu and nu, one way to think of what you're doing is that you're just taking the columns and deciding whether they should live on the left-hand side of the wall or the right-hand side of the wall. And I'm saying here that for the bipartition to arise in this context, you need to do that in a balanced way with regards to the odd columns. You need the same number of odd columns on both sides of the wall. But actually, if you thought of that in terms of rows instead, it would naturally be what you'd get if you thought of sign tableau, where if you, for instance, took sign tableau of signature NN, so that means you have a diagram with 2 n boxes and you have to fill them in across the rows with pluses and minuses so that you have n pluses and n minuses in total. So again, for that balancing to work out, to have the same number of pluses and minuses, it means for every, the number of odd rows that start with a plus has to equal the number of odd rows that start with a minus. And then as long as that's true, you can do what you like with the even rows because every even row has the same number of pluses and minuses automatically. So actually this subpost set that we reckon is involved in this cell classification of Qn is dual to the post set of sign tableau of signature NN. And that already arises in one of these cell classifications. That parameterizes cells of GLN cross GLN equivariant simple perverse sheaves on the same flag variety as we're talking about, GL2 and mod B. So that's, in terms of real groups, these are the cells corresponding to the real group UNN. And so that's dual to the post set which seems to classify the cells in this case. And this looks an awful lot like Vogel duality. Vogel has this list of dualities between these various post sets classifying cells for different real groups. And this seems like another such thing. The funny thing is that you sort of have an enhancement or an exoticness on one side of the picture. Here you've multiplied this flag variety by a vector space. But on the other side of the picture you don't. This is just the ordinary flag variety with no vectors floating around or anything like that. So it's all a bit mysterious, and I don't know why there should be this duality between the picture that we're conjecturally finding here and the well-known picture for UNN. So that remains to be discovered. And I've actually run out of things to say a little early, so that's it.
Any questions? Comments?
I was just thinking, you know, if you look at the usual nilpotent variety or unipotent variety, Lustig and Spaltenstein, they define the special unipotent pieces.
Yes.
Is there something like this here?
Yes, a good question. So this is something that a student of mine is currently looking into. So as I mentioned, it does seem to be a very natural thing to consider the orbits which correspond to special representations of the Weyl group. And that post set does seem to be self-dual. And then what my PhD student is looking at is whether you can then define special pieces properly so that above every orbit there should be a minimal special orbit. And then so you can allocate the orbits to special pieces. And then, of course, the next question would be to try and work out whether those special pieces were smooth, for instance. I mean, in the calculations that Pramod and I have done, it seems that they are rationally smooth. I mean, since we know the IC polynomials, we can check that as far as is computationally feasible. So those special pieces seem to be well defined, and they seem to be at least rationally smooth. But maybe they're actually smooth, and maybe that would be another way in which this enhanced nilpotent cone was like the ordinary nilpotent cone on type A in some sense that, yeah.
Any other questions? So if not, let's thank